Just a quick review of the things we learned till now before going through the power plant cycles. In previous sections, we had learned the fundamentals of thermodynamics, heat transfer, types of heat transfer, properties of steam, and how steam is generated. Now we will see how the work is developed by steam to rotate the prime mover when it undergoes through various processes in a cycle, and our main focus will be on Carnot cycle and Rankine cycle. This slide shows the arrangement of main components of thermal power plant. So you can see here there is a boiler where heat is added by the combustion of coal, and the water gets converted into steam. This developed steam then passes through turbine. While expansion in turbine, the work is developed, and this steam after expansion goes through condenser, where again it changes its phase, and the steam or vapor get converts into liquid, or that is condensate, and this condensate is now again pumped and it is sent to the boiler. So this is a cyclic process. Pump consumes some work to pump this fluid to the boiler. So now we will see our the first cycle, that is Carnot cycle. This is the ideal cycle, and any heat engine which operates on Carnot cycle will be having maximum efficiency. So first we will see this cycle on pressure volume diagram, and then we will see it on temperature and entropy diagram. We will see this cycle with reference to its application for steam thermal power plants. The Carnot cycle consists of two isothermal processes and two reversible adiabatic or isentropic process. So in this cycle, when we are seeing it on PV diagram, so 1 to 2 is isothermal heat addition, then 2 to 3 is isentropic expansion which takes place in turbine. 1 to 2 is heat addition that takes place in boiler. 3 to 4 is heat rejection, that is again your isothermal process. As you are aware that in isentropic, that is also known as reversible adiabatic, no heat exchange takes place between system and surrounding. So in this Carnot cycle, all the heat addition or rejection will take place across the isothermal process, that is 1 to 2 and 3 to 4. And this 4 to 1 is again isentropic compression, or that is reversible adiabatic compression, or that is pump work. Now we will see the Carnot cycle on TS diagram. So just refer this figure also. The process 1 to 2 is isothermal heat addition in boiler. So here you can see that the water enters at condition 1 in boiler and it comes out as dry saturated steam with a state condition of 2, and this heat addition is at constant temperature. Now the generated steam at state condition 2 expands in turbine to an state condition 3. This you can see from this TS diagram, that expansion from state 2 to 3 in turbine, and work can flow across that isentropic process. So 2 to 3 is expansion process, and in this process turbine develops work, so that is shown by W23. Then after expansion, that steam goes to condenser. So the inlet condition of condenser is 0.3. The expansion of steam takes place in wet zone, that is represented by point 3. Now that steam enters condenser at point 3, and after getting condensed it come out at point 4, and again it is a wet condition. So at point 4 there will be a mixture of vapor and water. Now that mixture is pumped by pump from state condition 4 to 1 isentropically. So pump will consume some work. So that is represented by W41. So again just see this total process, that from 1 to 2 there is a heat addition in boiler, 2 to 3 is expansion, isentropic expansion in turbine where work develops. Then 3 to 4 is condensation process that takes place in condenser where heat is rejected, and this process is isothermal process. And then 4 to 1 is the pumping work, and that also take place isentropically. Now we will talk about the efficiency of Carnot cycle. So efficiency is given as output upon input. So here output is net work and input is net heat added in the system, heat added in boiler. So net work done will be given as work produced by turbine minus work consumed by pump to pump the mixture to the boiler, and heat input is heat added in boiler. So this can be given by this expression, that net work done is work developed by turbine W23 minus work consumed in pumping, that is W41, and divided by total heat added in boiler. And these temperature limits, that TA and TB, because this is isothermal process, so this TA represents the temperature of boiler and this represents the temperature corresponding to the condenser. So this efficiency finally comes in respect of the temperature limits, that is given as 1 minus TB, the lowest temperature, upon TA, that is highest temperature. From this you can see that the efficiency of Carnot cycle increases with increase in TA. So as much as heat will be added the high temperature, the efficiency of Carnot cycle will be more. Now we will see that what are the practical difficulties in using Carnot cycle, because Carnot cycle is an ideal cycle, it is a hypothetical cycle, but we will see why it can't be used for our steam power plants. So the first thing you can witness here, that boiler operates in wet regime only. So point 1 condition is dry saturated liquid condition, 2 is dry saturated. So the boiler operation is basically heat addition is only in wet zone. As heat addition is here at constant temperature, so only latent heat can be absorbed. Total expansion through turbine in wet regime. Point 2 is dry saturated condition at the inlet of turbine. So the expansion takes place in the wet zone, and as you know that the turbine runs rotates at very high RPM. So these water droplets may hit the turbine blades, and that may cause the erosion of the blades, and in turn it damages the blades. Second problem is that the inlet condition of the pump here, that is a mixed phase, the mixture of liquid and vapor. So it is difficult to operate or to handle the pump, the mixed phase fluid, and compression or pumping of water and vapor mixture is thermodynamically unstable. That will require a very large volume of compressor, which is not economically viable. And one more thing you can see here, that the work absorbed or work required for pumping and work developed by turbine are comparable. So it is not economical also. This we can see here also what we discussed. So boiler operates in wet regime and maximum temperature is limited to 650 K. So efficiency of cycle is severely constrained. So to overcome all these difficulties what we faced with the Carnot cycle and its application for steam power plant, the solution or the answer is Rankine cycle. So all the limitations what we had witnessed, that has been charted out in Rankine cycle. So just a quick review of the processes that took place in the thermal power plant, which we had already seen in our earlier discussion during coal to electricity. So the purpose of boiler drum is to separate the water and vapor mixture because of density difference. That vapor takes the upper space and water again through downcomers, they comes in the bottom ring header, and through it goes to riser tubes. Because these downcomers are positioned in the non-heated zone and riser tubes are in heated zone. So because of the density difference, the natural circulation of water takes place. Now that steam which is separated in boiler drum is taken and passing through superheater, finally the main steam enters to the turbine, high pressure turbine. Then after expansion, as a cold reheat, it passes through reheater, again becomes the hot reheat. It is fed to the intermediate pressure turbine, from where it directly goes to LP turbine. After expansion in LP turbine, that steam passes through the condenser where it gets condensed, its phase changes from vapor to liquid. Then that liquid condensate is handled by CP condensate extraction pump. Then they are passed through LP heater where the sensible heating or regeneration takes place. Then from here it is sent to the deaerator. From here it is sent to the deaerator where by heating the dissolved gases are removed from deaerator through BFP, and after passing through BFP then through SP heater and passing through economizer, it is finally again sent to the boiler drum, and this cycle is repeated. So one half of the cycle consists of boiler and its auxiliaries, and the other half is the turbine cycle, which consists of turbine, generator, condenser, feed pump, boiler feed pump, and feed water heaters. In condenser, which is basically a large surface type of heat exchanger, steam is condensed by transferring its latent heat of evaporation to the cooling water. The condensate is pumped by condensate extraction pump from condenser. The condensate is collected in hot well and passed through the low pressure regenerative feed heating system and deaerator, where steam is used for heating and dissolved gases as O2 and CO2 are removed. Boiler feed pump sucks water from deaerator and pumps to boiler drum via HP heater. Earlier we discussed about the Carnot cycle. There were practical limitations, or you can say the problem associated with Carnot cycle. That's why it can't be used for steam power plant. The main thing was that the expansion, here you can see that in turbine was mainly in the wet zone. So it leads to the chances of blade erosion, and the inlet condition to the pump is also in mixed zone, or it is in mixed phase, that is liquid and vapor phase. So pump has to handle the mixture of vapor and liquid, which will require a compressor of size and cost comparable with the turbine. It would also absorb the work comparable to the work that is developed by turbine. So not much of benefit. And also, as that compressor has to handle, or the pump has to handle the mixed phase fluid, so its life will be also shorter because of the cavitation and blade erosion problem. So to overcome all these problems, a Rankine cycle has been developed, and the modern thermal power plants basically works on modified Rankine cycle. And one more problem, thermodynamic problem, was associated with Carnot cycle, that heat addition in boiler was at constant temperature. It means only latent heat absorption. So these problems actually limits the use of Carnot cycle. Now we can see this thermal power plant process over TS diagram. This is simple Rankine cycle. Here the problem, earlier problem which was associated with Carnot cycle, that is the wet expansion in turbine, still remains same. However, in condenser, the liquid or the steam is condensed up to the saturated liquid condition, that is point A. You can compare it earlier. After the condensation in condenser, the state condition of the state condition used to be the mixed phase. So now the problem which was with the pump, that has been eliminated in this simple Rankine cycle, that the pump has to now handle only single phase, that is liquid. So A to B shows the pumping work here. Then second problem which was associated with the Carnot cycle, that heat addition was only at constant temperature, or only you can say that is latent heat addition. So here the heat addition takes place both in form of sensible heat and then latent heat. One more thing we would like to see in TS diagram, that this 1-2 line shows the boiler temperature and pressure, and 3 to 4 represents the condenser temperature and pressure. So the area under this line on TS diagram, this total area shows the total heat addition, and area under this line 3-4, that represents total heat rejection. So net this area shows the work done. So when we will compare this Carnot cycle with the Rankine cycle, we can see by adopting these methods or condensing that steam up to the saturated liquid zone, we are getting extra work. So in this way we can say that a power plant working on Rankine cycle will develop more work done in comparison with the Carnot cycle. So here we can see that line E, A, B, C, D, F on this TS diagram represents the heat input in boiler, this total. The area A, B, C, D, that is the net area, represents the work done by the cycle, and line A, E, A, D, F represents the heat rejected. So total heat addition minus heat rejected gives the net work output of the cycle, and the thermal efficiency of the cycle is given as work done, that is area A, B, C, D, divided by heat added in the boiler, that is area E, A, B, C, F, C, D, F. So graphically also we can find out the efficiency if we can represent the thermal power plant process or the Rankine cycle. So this process 1 to 2, that is pump work, is reversible adiabatic compression at pump. 2 to 3 is heat addition at constant pressure. 3 to 4 is expansion of steam, isentropic expansion of steam in turbine, and 4 to 1 is condensation or heat release at constant pressure in condenser. So this 1 to 2, that is isentropic process. That's why it will be a line parallel to the axis representing temperature, because entropy remains constant. So 1 to 2 is a straight line. Then this is a sensible heating, and then latent heating up to this point, that is dry saturated steam condition. Then further when we are adding heat, the steam will get superheated. So that is point 3. It is represented by point 3. And from point 3, steam gets admitted into turbine where it expands and finally reaches to the end state of 4, which is still in wet zone. And this is also the entry point of condenser where the steam gets condensed finally in form of saturated liquid, and this cycle get completes. So the same thing you can see here, that is form isentropic compression. Because it is isentropic process, so there won't be any heat transfer between system and surrounding. Boiler, there will be a constant pressure heat input. Turbine, again it is isentropic expansion, so no heat transfer. Condenser, again there is a constant pressure heat release. This figure actually shows the different processes involved in Carnot cycle and Rankine cycle simultaneously on a same TS diagram. So from here we can see that Rankine cycle develops more power at the expense of additional heat transfer in boiler. Here you can see that is additional heat transfer in boiler. Hence efficiency of Rankine cycle is less than that of Carnot cycle, because efficiency is given as output upon input. So definitely we are developing more power, but on the cost of putting more heat input. One more thing you can visualize here, that as much as we can increase the boiler pressure, so this will move in upward direction, and as much as we can decrease or we can lower the condenser pressure, this will move in downward direction. So as much as the boiler pressure and condenser pressure may be kept apart, this enclosed area will get increased and we will get more work done, or we can say we will get more cycle. Earlier we had seen the simple Rankine cycle. Now we will see the possible modifications which will improve Rankine cycle efficiency. So the first thing is to increase the mean temperature of heat addition to the extent possible and lower the mean temperature of heat rejection as much as it can be done. So by lowering the condenser pressure, we can achieve the lowest average temperature of heat rejection. So here you can see that 1,4 line represents the earlier, or that is P4 pressure represents the earlier condition of condenser pressure. Now once we are lowering it, so as we had discussed earlier, lowering means we are moving in downward direction. So this 1-4- represents the new condition, or that P-4 pressure, because this is a constant pressure process which is less than this P4 pressure, represents the new condition of condenser. So we can see from here that by lowering the condenser pressure, we are also lowering the mean temperature of heat rejection, and this colored area of the diagram represents increase in net work output. Earlier the work output was this much only, this much. Now we got additional increment in the net work output as a result of lowering the pressure from P4 to P-4. In this process, you can see here that there is a slight increase in heat input requirement, which is represented by an area below this curve 2-2, but which is very small, and the work output what we are getting is more in comparison with this increment in heat input. So by doing this, that is lowering the condenser pressure, in turn we are increasing the cycle efficiency of our Rankine cycle. So this is the first modification, that is we can lower the condenser pressure to increase the thermal efficiency of Rankine cycle. So in thermal power plants, the condenser operates well below pressure in comparison with the atmospheric pressure. But now question arises that up to what extent we can lower this condenser pressure. So there are certain limitations. So P condenser cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. At the lower condenser pressure, there are possibility of ingress of air into the condenser, which will break its vacuum. Here also one thing we can see, in earlier condition, when the expansion or the condenser pressure was at P4, the expansion in turbine, final expansion in turbine was at 0.4 condition. The 0.4 represents the exit condition or final expansion state to turbine. So when we are lowering this condenser pressure, so you can see this 0.4 has shifted to 0.4 dash. This 0.4 dash is in more wet zone. So the lower condenser pressure increases the moisture content of the steam at the final stage of turbine. And this presence of large quantities of moisture is highly undesirable in turbines because it decreases the turbine efficiency, and by the heating of these water droplets, there may be chances of erosion of the turbine blades. Second modification in Rankine cycle is that superheating the steam to high temperature without changing the boiler pressure and condenser pressure. This also increases the overall cycle efficiency of a Rankine cycle. We can see by increasing the degree of superheat, this 0.3 shifted to 3 dash, and we are getting extra work done, which increases the overall work output of the cycle and hence increases the cycle efficiency. By this, we are increasing the mean temperature of heat addition. One more benefit we can see here, by increasing the degree of superheat, after expansion in turbine, the moisture content at the turbine exit also get reduced. So earlier when it was expanding from 0.3 to 4, this 0.4 represents that more moisture content. Here this 0.4 has shifted to 4 dash when we are doing more superheating, and expansion takes place from 3 dash to 4 dash. Now question arises, up to what extent we can superheat, so that is controlled by the metallurgical considerations. Now third option, for increasing the cycle efficiency is to increase the boiler pressure, which means by increasing the boiler pressure, we are increasing the mean temperature of heat addition, which leads to the increase in cycle efficiency, which we had seen in our earlier discussion, that efficiency in terms of temperature is given as 1 minus T lowest upon T highest. So once the mean temperature of heat addition is increases, overall cycle efficiency also gets increased. This increased boiler pressure also increases the boiling point temperature, but there is a drawback of this increasing boiler pressure. You can see from this figure. This is the earlier boiler pressure where it was going like this from point 3, again it was expanded into turbine. So this point 4 is nearer to the dry saturated steam condition. Once we are increasing the boiler pressure, so this superheating ends at 3 dash point, and from that 3 dash steam expands in turbine, and the final stage of the exhausted steam from the turbine is 4 dash, which has now shifted towards left, or you can say this 4 dash condition lies in more wetter zone in comparison with the state condition at 4. But this can be corrected by applying the reheating of the steam after partial expansion and again bringing it to the same T max temperature. The maximum moisture content at turbine exhaust is not allowed to exceed 12%, or the quality of steam to fall below 88%. You can see here from this figure, by increasing pressure we are gaining the net work output here, and there is a decrease in net work because of increase in boiler pressure. So overcome this problem, the best solution is to adopt the reheat cycle, which will increase the overall cycle efficiency of a Rankine cycle. The certain point which has to be kept in mind, that maximum steam temperature up to which we can go depends upon the material used. Minimum temperature of heat rejection is fixed by the ambient condition, and minimum quality of steam at the turbine exhaust is fixed by the turbine blade erosion. As much as the exhaust will be in wet zone, the chances of blade erosion will be more. So the Rankine cycle with reheat, the goal is always to achieve the highest high temperature of heat addition. Our heat addition should be at the high temperature. The steam enters in the HP turbine after expansion. It passes through reheater, and again this reheated steam expands in the low pressure turbine or intermediate pressure turbine, depending upon the case. So the benefit what we are going to get here is improvement in cycle efficiency, because overall we are getting more net work output from the turbine. So this you can see from here, with increased in boiler pressure and with the reheat cycle, this portion, this much extra work we are gaining here, that leads to the increase in cycle efficiency. And one more advantage of reheating the steam is that this 0.4 dash, which was in more wetter condition, shifted to the right hand, or you can say that steam at the turbine exhaust is more drier in comparison with the without reheat Rankine cycle. So chances of blade erosion at point 4 will be lesser in comparison with when the exhaust condition of steam from the turbine is at 4 dash condition. So just a quick review. To increase the thermal efficiency of plant, additional steam reheat before turbine expansion is incorporated. Steam is partially expanded in HP turbine and after that again fed to reheater before expansion in IP, and from IP it goes directly to LP turbine, which we had already seen in our discussion when we were discussing for the coal to electricity, and we had seen the various circuits, especially the steam circuit. We had already seen in our earlier discussion. Moreover, in the reheat cycle, the steam which passes through the latter stage of turbine is at a higher temperature, hence resulting into lower moisture content in the exhaust steam as compared to non-reheat cycle. So this is the advantage what we are getting by adopting the reheat system in Rankine cycle. Second method to increase the mean temperature of thermal addition is regeneration process, that also leads to increase in thermal efficiency of Rankine cycle in comparison with the simple Rankine cycle. You can see from this figure of the simple Rankine cycle that from this 2 to 2 dash, the temperature at 2 is very low, hence the mean temperature of heat addition is also low, which results in lower thermal efficiency. So the solution to this problem, or we can say to increase the mean temperature of heat addition, is to increase the temperature of feed water. This is accomplished by extracting steam from the turbine to heat the feed water. This also we had seen in our earlier discussion, where we were using LP heaters and HP heater, where the feed water is sensibly heated, and for heating the extraction are taken from LP turbine and IP turbine and HP turbine. So this process of heating the feed water before sending through the boiler by extracting steam from the turbine is known as regeneration. So this process we can see here, the condensate from hot well is extracted by condensate extraction from CP, and at point 2 it enters the LP heater and it is sensibly heated up to point 3. In sensible heating there won't be any phase change, only there will be a change in temperature. Now here at point 3 the steam, the feed water is taken by boiler feed pump and it passes through the boiler feed pump, it passes through the HP heater, again in HP heater it is sensibly heated. So you can see here that this total process is actually increasing the mean temperature of heat addition, and this results in increased cycle efficiency. So in all the process, one thing that is common we are seeing here, that anyhow we have to increase the mean temperature of heat addition, which will result in improved cycle efficiency. So regeneration process is also doing the same thing. The regeneration what we discussed just now, that also leads to reduction in irreversibility and it increases this cycle efficiency. So the modified Rankine cycle is that Rankine cycle which adopts reheating and regeneration process. and both the process, when we are adopting it, improves the cycle efficiency. Just a quick overview of feed water and steam flow during power generation process. And next, we will analyze the modified Rankine cycle for a 210 megawatt power plant, and there we will observe the key points of reheating and regeneration process. So here also we will see the components where regeneration and reheating takes place, which we had discussed in detail in our earlier slides. So here you can see the condensate, or that is feed water, is extracted by condensate extraction pump. It passes through LP heater where the first regeneration process takes place. For heating it, the extraction comes from LP turbine. This extraction is coming from LP turbine. So here there is a sensible heating of feed water. Now this feed water goes to the aerator where again it gets heated to remove the dissolved gases, and this heating is done by the extraction taken from IP turbine. Now this feed water is extracted by boiler feed pump and through feed water heaters, HP heaters, that is high pressure feed water heater. This goes to the economizer, and finally this comes to the boiler drum where the two phases get separated. So first point, that is regeneration, is taking place in these heaters where the feed water is only sensibly heated so that its mean temperature of heat addition can be increased, which leads to the increased cycle efficiency that we had already discussed. Second is that we will see the reheating. So once that steam that is coming out from the boiler drum passes through the superheater and the main steam comes out, it enters the HP turbine. After expansion, its pressure and temperature get reduced. This is called cold reheat. This cold reheat again passes through reheater. So this is a reheating process which we had already seen in our reheat Rankine cycle. Then this reheated steam, which attains the same temperature of the main steam with reduced pressure, enters to the IP turbine where it expands and then it is fed to the LP turbine. So this is the process through which steam undergoes. So this is your reheating zone where steam gets reheated, and this is basically regeneration portion where regeneration or heating of the feed water takes place. Now we will see the modified Rankine cycle for a 210 megawatt power plant. We will see the various processes that is taking place and how the regeneration and reheating is. Now we will see that regeneration and reheating process on TS diagram. So here you can see that condensate at point 1 from hot well is taken by condensate extraction pump. So that is represented by 1, 2, that is isentropic pumping work. At point 2 it enters in LP heater, here you can see, and it is sensibly heated with the extraction steam coming out from LP turbine. During this sensible heating process, its temperature changes and the phase remains same, that is liquid. And this is regeneration process, and that regeneration is shown that extraction is coming from LP turbine, which is used to heat feed water in LP heater. This you can see that extractions are coming. Three extractions for 3 LP turbines, which sensibly heats feed water. Now feed water is get heated with the help of extraction from IP turbine in deaerator, and this point 3 shows the inlet condition of the boiler feed pump. You can see here this is point 3. Now 3 to 4 shows boiler feed pump work, BFP work, that is also treated or assumed as isentropic. So that's why a vertical line, it is represented by a vertical line on TS diagram. 4 point shows the inlet condition at HP heater. Now this 4 to 5 process is sensible heating in HP heater with the help of extractions coming from HP turbine and IP turbine. So in HP heater, for heating we are getting extraction from IP turbine and HP turbine. One extraction of IP turbine is going to the deaerator. So 4 to 5 is HP heating process. Then 5 to 6 is process happening in economizer, and this you can see the pressure is 150 kg per centimeter square and temperature becomes 320 degrees centigrade at 0.5. Now it starts changing its phase at 0.6 is the dry saturated steam condition, which represents the boiler outlet condition, or that steam coming out from the boiler in dry saturated condition. Then it passes through superheater. You can see here this passes through superheater. So this process is represented by 6 to 7 over TS diagram. Then expansion takes place during the superheating. This temperature increases from 320 degrees centigrade to 540 degrees centigrade. That is the main steam parameter. That is pressure is 150 kg per centimeter square and 540 degrees centigrade. And you are aware that this steam generation process is a constant pressure process. So pressure remains constant. Now the superheated steam at the condition of 0.7 enters into HP turbine and expands up to point or state condition 8. This expanded steam with reduced pressure and temperature is again sent to the reheater. So this you can see this is a reheating process. 8 to 9 is your reheating process. In this reheating process, the steam temperature is again brought to the main steam temperature, that is 540 degrees centigrade, and from state condition 9 the superheated steam expands into IP turbine. So this you can see that 540 degrees centigrade and 35 kg per centimeter square. At this condition the steam enters into IP turbine where it expands up to 0.10, and then it is directly fed into the LP turbine. So you can see that further expansion takes place in LP turbine. So this point, or that is the outlet of 11 point, represents the outlet or exhaust steam condition from LP turbine, which is in wet zone. So partial, the expansion in LP turbine is allowed in wet zone. So 11 point represents the inlet condition to the condenser. In condenser, the exhaust steam from LP turbine loses its latent heat and the phase changes from steam to dry saturated liquid condition, that is 1, and again this cycle is repeated. With this I hope that it clears the concept of modified Rankine cycle, the various processes that takes place, how that reheating and regeneration takes place, and this reheating and regeneration, how it improves the overall efficiency, thermal efficiency of the cycle. So now a quick recap of our earlier discussion with help of animated power plant cycles, which is developed by L&T S&L, and here we are using it for only academic discussion. So this is Carnot cycle. Already we had discussed it. This is isothermal heat addition in boiler, isothermal heat rejection process in condenser. This is isentropic expansion in turbine, due to which the work is developed. This is isentropic pump work, and the Carnot cycle efficiency is given as output, that is work done, upon input, that is heat added into boiler. Then comes simple Rankine cycle. The superheated steam from boiler passes through turbine. Here you can see the superheated steam passes through the turbine, expands and goes to the condenser, where it loses its latent heat and phase change occurs, and steam gets converted into saturated liquid condition, from where it is pumped into boiler. In boiler, the water first sensibly heated up to the saturation temperature, then it changes its phase by absorbing latent heat in boiler, then further it is superheated, and this process completes a cycle. So this total completes a cycle, and efficiency is again given as net work output. So W1 minus W2. W1 is the work produced by turbine, W2 is the work consumed by pump, divided by heat input that is given into the boiler. Due to irreversibility into system, this isentropic expansion or compression is not practically possible. So instead of that, this will be adiabatic compression and adiabatic expansion. So this represents the actual Rankine cycle. This is reheat Rankine cycle. All these processes are same what we discussed earlier. So the superheated steam expands into HP turbine. Superheated steam goes to turbine, expands, and after expansion it passes through reheater, and after reheating, the temperature of reheated steam matches with the main steam temperature, and this reheated steam again sent to the LP turbine, where it expands. Then after expansion, the exhaust steam goes to a condenser, where it get converted, the steam is converted into liquid. Then again this condensate is extracted by condensate extraction pump. Then it is through economizer, it is sent to the boiler drum, then superheater, and this cycle completes. Then comes the regeneration process. So here you can see, already we had discussed it. So this condensate through CP, and after passing through LP heater is not shown here, goes to deaerator. From deaerator, it is taken by boiler feed pump, then through HP heaters. It, after passing through economizer, it goes to boiler, where that steam is separated from the liquid or water. Again it is sent back to the superheater, from where it goes to the HP turbine for heating in deaerator. Extraction comes from turbine, and like this cycle completes. So these diagrams are just a tentative representation. Already in detail we had discussed in earlier discussion. This is reheat and regeneration cycle. With this, we come to the end of the topic steam generation and steam cycle for steam power plant. I hope that this discussion has developed insight to understand the working process of thermal power plant. Thank you for hearing with patience. Feel free to ask your doubts and queries by sending a mail over rvashaspati@gmail.com. So I am here, Rajneesh Vashaspati, Deputy Director, National Power Training Institute, Eastern Region, Durgapur. Thank you very much again to all of you. Have a good day.